So we're going to start by taking a look at an example in my GitHub repository in the Java 8 folder. And this is going to be the EX16 example. And I'll upload a video of this, which will show where to get the code in case you want to play around with it. So this particular program implements various ways of computing factorials for big integers in order to demonstrate the performance of alternative parallel and sequential algorithms, as well as the danger of sharing unsynchronized state between threads. And it also shows off Java streams, both sequential and parallel streams, and it shows off a few of RxJava's features as well. We aren't really covering RxJava, so I won't spend much time on that. So the way you would do this with kind of classical parallel streams using a long value would look something like this. You'd say long stream, range closed from the value 1 to n, run the stream in parallel, and then use the reduce terminal operation to multiply the pairwise values together to end up with a single reduced result. The problem, of course, is there's exponential growth rate of factorials. So you'll end up very quickly going way beyond what you could possibly get or you could possibly do if you use long. So instead, we're going to use big integers here. And you can see some other fun examples with big integers here at this link as well. So here's the program. It's going to run 20,000 times, and we're going to have a default factorial number of 1,000. So it's going to compute 1,000 factorial, which, believe me, is a very large number. Just for kicks, we're going to start running this thing in the background because it takes a while to run, and we'll look at the code. So the first thing we're going to do is we're going to figure out what the n should be here, which is either going to be the default, which was this 1,000, or we can provide a command line argument if we want to give it a non-default value. We then go ahead and warm up the fork join pool so that all the parallel processing will run as smoothly and efficiently as possible. And then we're going to run a bunch of tests, and we're going to take a look at each of these tests in turn. We're going to run a sequential stream factorial test, which will kind of be the simple one that just uses a sequential stream. We're going to do a sequential RxJava implementation, which we won't spend too much time on because we aren't really covering RxJava. For fun, we're going to run a buggy parallel factorial, which is very fast, but produces the wrong results, so it's not very useful. We're going to do a parallel stream factorial, which uses parallel streams in a much better way. We're going to show an alternative way of doing parallel streams. And then we're going to show an RxJava parallel flowable implementation. And then finally, just for fun, a really, really inefficient synchronized parallel factorial. And when we're all done, we will go ahead and take a look at the results and sort them by best to worst. Let's go ahead and take a look at these one at a time. So here's buggy factorial, and it's got an inner class called total, nested inner class called total. And this has a multiply method that multiplies this field called mtotal, which is a big integer, by n, which is the parameter that's passed in. And down here, we have the factorial method on buggy factorial. You can see it makes one shared copy of total, which, by the way, is not synchronized in any way, shape, or form. And then it puts it into a parallel stream. So it's going to go through the value from 1 to n in parallel. It'll map each of the big integer, or each of the longs to a big integer. And then it will use the for each terminal operation to multiply t, which is the instance, the one and only instance of total. And of course, chaos and insanity will break out because this is not synchronized. And so it'll run quickly, but you'll get the wrong answer. And we'll see what the wrong answer is when we look at the results. And we'll return the total, which is also not synchronized. So just badness galore. Let's take a look at a better way to do this. This is the synchronized parallel factorial. And this is a better way from the point of view of correct behavior, but it's going to be really, really slow for reasons that will become clear in a moment. What we do here is we use the same nested total class, except this time we're going to have the multiply method using a synchronized statement in order to protect the mtotal field. And so that mtotal field will now not suffer race conditions, so we'll get the right result, but as you'll see, it's going to be really slow. We also have a get method that does a synchronized retrieval of mtotal as well. Here's what the code looks like. this code will work correctly, but as you'll see, it's very inefficient because we're synchronizing things wildly and unnecessarily. Here's the parallel streams implementation. This is the right way to do things. It's also the fastest way to do things. So we go from 1 to n in parallel, convert everything to a big integer, and then we use the reduce method, which will multiply each operation or each value together, each pairwise value together, till we finally reduce it to a single reduced result. And the nice thing about this is there's no shared state. It's very efficient. It does all the splitting and applying and combining transparently to you through the magic of parallel streams. And it's really the right way to do this. There's another alternative way of doing this with parallel streams that uses the 3-parameter version of reduce. And as you'll see, the performance is roughly the same. Once again, there's no shared state, so that's good. There's a couple of examples here that use things called Java Rx Streams, or sorry, not Rx Streams, RxJava. And RxJava basically has the concept of what is known as reactive streams. And what we do here is very similar to what we do with Java streams. We create a range of values, turn it into a parallel, flowable as it's called, convert the longs to big integers, and then we use the reduce method to multiply everything together, and then we wait until all the results are done. So this isn't really a course on reactive programming, but it's just fun to compare and contrast the different ways of doing things. Here's the sequential streams implementation of this. It looks just like the parallel version, except there's no call to .parallel, but otherwise it's identical. And then here's another RxJava version that's sequential. And again, I won't talk about that, but that's another way to do things. Here's the run test method. As you can see, we come in here, we garbage collect so that all the memory is available. We use the little time run helper method in the run timer class, which starts the timer, runs the run, and stops the timer, and then stores the results into the underlying hash map of results. And after we're done doing this, we then print out what the results of the factorial were. And that's basically it. So with that, let's go look at the performance of these things. And first, I'll just show you something interesting. So you'll notice that this prints out the value for a factorial of 1,000. It goes on and on and on. It's pretty huge, as you can see. And they're all the same, except for the one that's the buggy version. And you can see that, as you'll see, it's pretty fast, but it's buggy. So what's the point, right? It doesn't do you any good to be fast if you get the wrong result. Here's the sorting of the results. You can see that the parallel stream factorial was the fastest, and it was about 7 times faster than the synchronized version that used that synchronized statement that protected the M total field. And the fact that it's about 7 times faster to do it in parallel should give you an important hint. I have an 8-core, 8 hyper-threaded multi-core processor. And so the parallel streams version was basically just humming along, pretty much, doing linear time performance, running on different cores to do this. Whereas the synchronized parallel factorial had a bottleneck. So even though it had a bunch of cores that were running, it was having a single point of contention, which was that lock. So we were basically kind of single threading it, if you will. So it performs really, really slowly. You can also see that the buggy factorial was pretty fast, but of course it got the wrong results. And then the sequential stream factorial was slower than the parallel stream factorial. Interestingly enough, if we had a low value for n, like if we were doing the factorial for the number 20, the sequential version would probably have been faster because it takes a while to do parallel processing, if you recall. So you should only use parallel processing when n is big or q is big, where q is the amount of processing you do. And computing a factorial is fairly computationally intensive. So we get a nice speed up here by using parallel processing. Okay, let's see, some questions.
Sorry, I might have missed why the buggy version is buggy. I mean, just an out of order multiplication wouldn't be the bug.
Oh, no, of course not. Well, I mean, it could be the bug, but the problem there is that remember we've talked before about how unsynchronized or mutable shared state is the root of all evil in concurrent programming. So this is a great example of mutable shared state. So this is mutable, right? M total equal M total multiply N. So that we're mutating the value of M total. That's being done in multiple threads. Because we have no synchronizers here, different threads running on different cores are going to be processing and accessing the M total field differently based on caching. And so they're going to be reading values that in fact are not consistent. So you'll just get randomly weird results. As we saw there, we got just randomly weird results. And that has to do with the fact that if you access, especially you change mutable shared state between multiple threads in a multi-core processor, chaos and insanity will ensue. And that's just the nature of the beast with modern multi-core processors. If you don't have synchronization, then all bets are off as far as what results you're going to get, because things will be non-atomic, things will be, the visibility of the values will not propagate between the core caches, and you'll end up with memory inconsistencies, you'll end up with out of order operations. So bottom line is either synchronize, which we did here, but then it was really slow, or better yet, don't require synchronization by partitioning things up in such a way where there's no need to synchronize. Synchronization is done through other means, like in the case of the reduce operation. These kinds of things. Yeah, I'm sorry, go ahead.
I'm sorry. It was going to be a question, but I can wait.
Yeah, not a point, go ahead.
So just curious, what does reduce do behind the scenes to synchronize it that also makes it so much quicker than putting in an actual synchronized lock?
Yeah, so if you watch some of the videos, there's some videos probably week 7 or week 8 that talk about how reduce works with the parallel streams implementation. What it does behind the scenes is it will run the data in its own core, and then the way it works under the hood is it uses the fork join pool. And so one thread will fork one task will fork another task. Both those tasks will run in parallel, and then the parent will then join with the results of the forked child. And that join operation, which is always done in one thread, so there's no synchronization required, will have an appropriate, what's called a fence, something that will flush the cache, or a barrier, I guess is a better word, a barrier that will flush the cache appropriately so that you'll get the latest value. And that gets into something called happens before relationships. We don't really talk about happens before relationships in this course, but if you take the companion course, which is the concurrent object-oriented programming course, you can learn all about happens before relationships. And in fact, if you are impatient and don't want to wait for that, you go over here to my YouTube channel and you go look at concurrent object-oriented programming. Here's a good example of that. This is a playlist, and then we search for happens. So you can find out about happens before relationships, and that'll explain how all this stuff works under the hood. It uses barriers that are put into the Java virtual machine in other ways.
Interesting. Thank you.
Sure. Other questions?
Actually, one more question. If you were to substitute that reduce for, let's say, like a integer sum call, how would it have impacted the performance?
I'm sorry, say it again.
If you were to substitute calling reduce to just do like just like a collect within an integer sum to combine the results, or I guess that's what we did with the synchronized lock. So never mind. I guess there wouldn't be another way to do that other than synchronizing the variable. So never mind.
Well, I think to answer your question, I don't know if there's a product collector. There's a summing collector. I'm not sure if there's a product collector, but even if there isn't one, you could write one. You could write a collector that would sum results, so you could multiply the results together. So it would probably be roughly the same as the reduce, but since reduce already works, why bother? It would probably be more trouble than it's worth to write your own collector. That would be a lot of work.